Alrighty, welcome back to IAT 301, Engineering Project Cost Analysis. In this lesson, we're going to go through and review present and future value, just so that we can use it to build on as we go forward. After we get done with that, we're going to go through and introduce uniform payment series formulas and what they actually mean. And then finally, we're going to introduce gradient payment series formulas. As a warm-up example, I'm going to assume that we have a situation where we are investing $2,500 in some kind of an account at 6% interest for 10 years. And so let's go through and review how to do this. So let me switch over here to the DocCam. So in this example, we know that we have a present value, PV, equal to 2,500. We have an interest rate, I, of 6%, and we have a time, T, equal to 10 years. From the future value equation, we know that the future value, oops, sorry about that, future value is equal to the present value times F given P. We know what the present value is. We're trying to find the future value given the interest rate and the time that we're investing it. So in this case, we know that the future value will be $2,500 times the future value given the present value at a 6% interest rate and a time of 10 years. In this case, we're compounding annually, so what we need to do is make sure that so this is a straightforward problem. If we were compounding on an interval other than annually, then what we would have to do is divide the interest rate by the number of compounding periods per year, and then multiply the number of reinvestment periods by the number of by the number of periods we're reinvesting per year. Okay, so in this case, what we know is that since this is equal to the present value times 1 plus the interest rate raised to the time, we can solve this using straight algebra. This becomes a calculator equation. So we have present value of 2,500 times 1 plus 0.06, that's 6% expressed as a decimal, raised to the 10th. So in this case, if I punch this into my calculator, what we end up with is 2,500 times 1.06 to the 10th gives us a total future value of $4,400 or $4,477. That means that the $2,500 today is equivalent to $4,477 in 10 years, if we assume an interest rate of 6%. Okay, so just a review, in this case, what our cash flow diagram would look like is we're sinking $2,500 in year 0. And in 10 years, that $2,500 is resulting in $4,477. Now, this is kind of nice because we see that, sure enough, that money does have a time value associated with it. Okay? But keep in mind that for a number of investments, we're not necessarily going to be looking at trying to invest or take out money in year 0 and see the benefits or cost of that transaction 10 years later. typically we're going to see a annual type of situation. And that's where we're going with this lesson. So just to summarize what we have, we know that, sorry about that, I got a little bit of coffee on my hand. We know that in the case where we have a future value, we can find that future value by taking the present value times 1 plus the interest rate to the number of reinvestment periods. And by throwing a little bit of algebra at this, we can solve for the present value. If we divide both sides by this term here, we can solve for the present value as the present value is going to equal the future value times 1 plus the interest rate to the negative t. Okay. If you look at the two columns on our table, and let me pull up the table for the 6%. We can see that the multiplier from this table for a 6% interest rate for the future given present is 1.791. So taking my calculator, 2,500 times that 1.791 gives us the exact same result. Now this is the really cool part of this, and I'm going to zoom in just a little bit on this. I'll have to zoom out here in a second. But what we see is that if we look at this present given future, that's the present value equation, we have a multiplier of 0.5584. Well, let's just do something. Let's take that 1.791 and put it in the denominator. So I'm going to take 1 over 1.791, and sure enough, we get the 0.5584. And this is a very fundamental relationship between each of these different payment series that we're going to be looking at. If we're looking at the future given the present and the present given the future, well, we see a reciprocal relationship between these two. In fact, we can simply say that the multiplier for the for either of these, so I'll just say that, well, let me do it this way. I will say that this future given present, IT, is nothing more than 1 over the present given future, IT. And similarly, and keep in mind that this would correspond with the multiplier. Geez, that's clear off the side there, isn't it? Okay, so similarly then, we can say that if we want to find the multiplier for a present value given a future value, that is nothing more than 1 over the multiplier for a future value given a present value, IT. So ultimately what we see by this is that if we know how to use our table, we could essentially cut the number of columns needed in half, because the same relationship holds throughout our entire table. We would only need to have the future given present column, and then we could calculate directly the present given future column. And subsequently, with each of these other columns, we could do the exact same thing. We could say that the annual given future is nothing more than the reciprocal of the future given annual, okay? And similarly throughout the rest of the table. Ultimately, what you want to do is very quickly get away from trying to memorize these formulas, as I have here. Let me move that over. In this case, what I have done is I know this formula because it's very nice and straightforward and easy to remember. However, as we move forward, this is no longer going to be the case. These formulas are going to become progressively more difficult to remember. Therefore, I strongly encourage you to move away from trying to memorize these equations and just use the tables. The tables are ultimately what you will have available when you enter the field. So, okay, so now let's take a look at a slightly more realistic problem. And let's say that instead of a single, sorry, I keep on getting this paper turned around sideways. Let's say that instead of a single cash flow, we have a situation where we have multiple cash flows. So we might have something that looks like this. Now, a person might ask what this would be representative of. And my answer to you is an auto loan, okay? In the case of an auto loan, you're requesting a present value, okay? So this might be the $10,000 that we need today, okay? And at the end of each year, which I know isn't particularly truthful in the matter, we would have a lump sum payment on that auto loan in order to pay it off. And what we want to have is a fixed amount that we pay each year that essentially will pay off this $10,000 over the course of the 5 years that we're paying on it. Now, one very important characteristic here is keep in mind that we are receiving the money at the beginning of year 0, okay? And then we are paying the first payment at the end of year 0, which correspondingly is the beginning of year 1. Then we are making the second payment at the end of year 1 or the beginning of year 2. In engineering economics, we usually consider the end of cycle analysis, okay? That means that when we see year 1 here, we are or see a element on a cash flow diagram, we are usually assuming that that occurs at the end of the previous payment period. So in this case, this negative cash flow in year 1 would have actually taken place at the end of year 0, okay? So let's go through and take a look at a situation like this. And let's see if we can't figure out how we can do this. I'm going to change up the example just a little bit. Let's say that instead of looking at a present value, at least for now, we're wanting to look at a future value. And this might be more in lines with a some kind of a retirement plan. So let's go through and say that we are making periodic deposits into an account of some sort. And we're hoping to receive a end of year or end of cycle benefit from these periodic investments. I'm just going to zoom in a little bit on this. Okay, so let's say that each year we invest $1,000. So we have a $1,000 contribution here, a $1,000 contribution in each of the subsequent years. So these would be year 0, 1, 2, 3, and 4, and we receive this benefit in year 5. This then would be our future value. Well, one way that we could go through and work this is by saying, okay, well, the future value of the first deposit that we made is in fact nothing more than the present value times the investment period. So we can go back to that future value given present value formula, okay? And then we can do this with each successive year. So we could say that in this case, in order to determine the future value, we can take the 1,000 times the present value given, the future value given present value of, well, let's just assume that this interest rate is 6% again, since that's the table that I have available. Okay, so we have an interest rate of 6%. And in this case, we see that our term is 1, 2, 3, 4, 5 years. So this would give us the future value of the first $1,000 that we invest. Now notice here that I am saying that the $1,000 is invested each year for the 5 years. Okay, what that means is that we have a uniform payment series here. So anytime we see the phrase uniform payment series, what that means is that we're making the same payment on an annual or periodic basis for a fixed number of terms, okay? Now I should make sure I clarify that, because even though I'm saying payment, it doesn't necessarily have to correspond with a negative cash flow as I have illustrated here. We could be seeing a net income per year, and we're wanting to figure out how much that would result in the future or anything else. So generally I will draw it this way just because, at least from a consumer point of view, we're going to see negative cash flows resulting in a future benefit if we're talking about a retirement account, or we're going to see a net present value with negative cash flows in order to pay off those consumer loans. Okay, so in this case, we see that the future value of the first $1,000 is nothing more than 1,000 times the future value given the present value at 6% interest for 5 years. To that, then, we're going to add the future value of the subsequent $1,000. In this case, we're going to re-perform the exact same calculation. We're going to say that we're taking that $1,000 and we're determining the future value given the present value in year 1 at a 6% interest rate for the 5 years. Now, I'm sorry, in this case we're going 1, 2, 3, 4 years, because we're looking at the $1,000 we invested in year 1. So this would be 4 years, and subsequently we would have the $1,000 invested in year 2, future given present at 6% for 3 years, the $1,000 times the future given present at 6% for 2 years, and finally the $1,000. There we go, that should be a little better for you. Times the future value given the present value at 6% for 1 year. And that will allow us to calculate the future value of this investment. So what we see then is, I'm going to kind of cheat here. I'm going to go through and calculate each of these. Well, actually, I will use the table. Okay. So the table says that the future value given the present value at 6% interest, and I'll zoom in just a little bit on this, for 5 years is 1.338. So the multiplier for a 6% interest rate for a term of 5 years is 1.338. So I have future value equal to 1,000 times 1.338 plus 1,000 times the multiplier for a 4-year investment is 1.262, followed by 1,000 times a multiplier of 1.191 plus 1,000 times a multiplier of 1.120 plus 1,000 times 1.06. Okay, So with this then, what we see is that the future value of this payment series, specifically of this uniform payment series, is going to be the 1,000 times the 1.338 times, or plus the 1,000 Give me a second, I typed that in my calculator wrong. So 1.338 plus 260 plus 1 plus 2 plus 6. So we find a total investment of $5,971. Okay. So the future value of this payment series is $5,971. Now what you might notice, and this totally makes sense, is that if we were to deposit $5,000, which is the sum of the five $1,000 investments, in year 0, and calculate the future value of that investment, it's going to be greater than investing $1,000 over 5 years. Okay? And that makes sense because for the full 5-year term, that $5,000 is going to be accumulating interest. In this case, however, if our budget doesn't allow it or we just can't make it work, we can spread that over the 5 years, make $1,000 investments, and still see a benefit from that investment for 5 years. Just keep in mind that it will not be as great as if you were to go through and make the initial investment up front. This is why a number of people say that you should invest a lot early in life, early in your career, because that early investment will benefit you much greater than later investments. If you have a big chunk of money sitting in your retirement account early in life, it's going to be able to perform a lot more work, generate a lot more interest for you than what it will if you invest later in life. Okay, so with this, what we see is that we are making annual contributions. Now, fortunately, somebody came along and said, this is rather tedious. So what they said, what they did was they threw a little bit of algebra at this, and they came up with a future given annual equation. So they can say that the future value, let me move that so it's visible. So the future value of some investment, given that we're depositing annual contributions to this, is the annual cost of that investment times the multiplier for the future given annual at the specified interest rate for the specified time. This looks almost identical to what we've already talked about. This is one of 4 equations that describe uniform payment series for us. As you might suspect, there is also an annual given future, and as you probably already guessed, there is a present given annual and annual given present. Now, I'm going to talk about this just real quick because what I want to do is demonstrate to you why I stated earlier that we're probably going to want to move away from memorizing and using the algebraic formulas for this and get much more into the feel of using our tables, or as the book advocates, the Excel functionality. Okay, I will warn you though, on the FE exam, you will be provided the tables, but you will not be allowed to use Excel. So it's going to benefit you significantly by at least spending some time using the tables. That way you're not overly dependent on Excel when you take that exam, because ultimately these type of problems are relatively easy to pick up points on if you just have some of the basic tools to understand what the problem's asking. Okay, so if we're looking at the future value given an annual contribution, the book states that that future value equation is equal to, let me find it here, is equal to the annual contribution times, I'm copying this straight out of the book, so give me a second, I'm wanting to make sure I copy this correctly. The quantity, 1 plus I to the t minus 1 all over the interest rate. So I'll rewrite that since that is a little bit hard to read. It is the annual contribution times 1 plus the interest rate raised to the time minus 1 all over the interest rate. Now, as I stated earlier, this is somewhat difficult to interpret, somewhat difficult to remember. And the reason for it is that unlike the future value, present value equations associated with single deposits and withdrawals, this one is not nearly as easy to interpret. We could actually derive it by going through and looking at this symbolically, going through and just using algebra to derive this equation, but we're not going to. That's really not the point of this class. What we're going to find ourselves doing is relying on the table or Excel to go through and solve each of these problems. So let's just revisit the previous problem. In the previous problem, we said that we had a future value and an annual contribution. We're finding the future value given the annual contribution. Keep in mind, again, this is set up so that we can see that the annual cancels the annual, leaving us with the future, which is what we're after, at the specified interest rate for the specified time. So in this case, we have future value equal to the $1,000 we're contributing annually, a future given annual at a 6% interest rate, and a period of 5 years. Okay? So from the table, I see that in the future given annual column, future given annual, we have a multiplier of 5.637. So we take that 5,000, or that 1,000 times 5.367. Let me verify that. I'm sorry, it was 637. 5.637. And when we multiply 1,000 by 5.637, we end up with $5,637. Now notice there is a slight calculation difference between here and here. The reason for this is because these tables lose some degree of significance. They round the results as they populate these tables. Similarly, I rounded these results that I took from the table. If I had went through and used the exact solution, we would have arrived at a much more similar solution. But we can see that this gives us a really good idea of what the future value of that payment series turns out to be. So let's go through and do a second example just so that we can so that we feel fairly comfortable with this. Let's say that we are let's say that we're going through and investing $200 quarterly interest rate of 4%, and we're investing that for 10 years. So T is equal to 10 years. So when we go through and set this up, we see that we're again searching for the future value given an annual contribution, and that we're finding the future given the annual at an interest rate. Now, notice that this is a quarterly investment. So we're going to take the annual interest rate and divide it by 4, because there are 4 payment periods in a, excuse me, if we compound quarterly. So we're going to take the 4% divided by 4 to get a interest rate of 1% compounded each investment period. And in this case, since we're compounding quarterly over 10 years, that means that there are 40 compounding periods in that 10-year cycle. So we have $200 times the future given annual contribution. And keep in mind that I say annual, but what this really, and the reason why we in engineering economics use annual is because most of the time these benefits or costs occur on an annual basis. For those of us who are consumers, we recognize that most of the time we make monthly payments to whatever we're working towards. But within engineering economics, this is generally payment on an annual cycle. Okay, so we have the 1% over the 40 periods. So we can look at our table for 1%, which is in this column. We are looking for the annual given future. So in this column here, go down to the 40th entry. I'm sorry, we're looking for the future given annual. So we have a multiplier of 48.886. And with that, then we know that we have 200 times 48.886 gives us a total future value in this investment of $9,777. Now, notice that this is significantly easier than going through and summing up all of the future value given present value equations as we did. When you go through and generate cash flow diagrams like this, where you have an excessive number of payment terms, it is perfectly acceptable to go through, do something like this, where you would list 0, 1, 2, 38, 39, 40, and notice here I kind of made a little bit of a mistake there, but that's okay, we can live with that. So in this case, you can just use a bunch of dots to illustrate that there is data there that just isn't being represented, and as long as you indicate that these are each $200 negative cash flows, you're more than good. Okay. If you go through and generate this with Excel, then it's not really that big of an issue, because Excel can go out and create this cash flow diagram for you very quickly. No excessive amount of work on your part, but if you're doing this by hand, this is more than acceptable. Okay, now let's consider a slightly different situation. Let's assume for just a second that we know what future value we need. We know that we are going to need $20,000 in, say, 10-year time. So 10 years from now, we need to have $20,000 available. And this could be for any number of things. Maybe that's how much our TV is going to cost that we want to buy in 10 years. Or probably more realistically, maybe that's the cost on a for maintenance on a piece of equipment at its 10-year maintenance visit, or something along those lines. So if we are able to invest money at, again, I suppose we have a 7% table here, for the 10 year, what annual contribution do we need to achieve? This is something that is much more common, or I shouldn't really say that. You run into this fairly frequently in engineering economics, because when you're making an equipment purchase, what you want to do is have a plan in place for maintenance and operation of that equipment. Okay, that means that you might have a $500,000 piece of equipment that you purchase and you pay cash for it, but you want to have enough money setting aside so that as maintenance comes due on that piece of equipment, you're able to pay for that maintenance without having a significant negative cash flow. You want to set the money aside now so that when that maintenance occurs, you are prepared for it. So let's take a look at this. We saw just a second ago that the future value is equal to the annual contributions times the future given annual at the interest rate and the payment period, in this case 10. We can say the exact same thing is true as we saw a minute ago. If we have a situation where we're looking for the annual contribution, then we can just divide both sides by this term, okay? And if we do so, we end up with a annual contribution equation that looks something like this. We have an annual contribution we're trying to find times the future value of annual given future at the specified interest rate and the specified time. Now, by throwing the algebra at this, we can see that this is exactly the reciprocal of what we just saw. This is, in fact, I, well, it is the future value times I over the 1 plus I to the t minus 1. That is the reciprocal of what we just stated for the future given annual equation. Sorry about that, I keep on forgetting to scoot over the paper. Okay, again, we're not going to memorize this. We're going to either use Excel or we're going to use our tables to solve this directly. We're going to look at the multiplier that we need in our Excel or in our tables and use that multiplier to figure out what we're going to multiply that future value by. Keep in mind that this is going to be a decimal value between 0 and 1. The reason for that is because we're finding an annual contribution, and that annual contribution is going to be a fraction of the future value we're trying to achieve. So let's just go through and plug this in. Okay? So in this case, if we look at the cash flow diagram again, we are trying to find A so that we have a future value available. So we can say that in 0, 1, and 2, and 7, and 8, I'm sorry, that would be 8, and 9. We have an annual contribution, and then we take out the money at the end of year 9, which is the beginning of year 10. Okay, so go ahead and set this up. We have a future value of $20,000, a annual given future at the 7% interest rate for the 10-year period. And from our table, we see that in the A given F column for the 7%, 10 years, we have A given F 0.0724. So our annual contribution is going to be the future value multiplied by our multiplier of 0.0724. And we find that the annual contribution needed is 20,000 times 0.0724. That means each year we would have to contribute $1,448 into an account in order to have the $20,000 available that we need at the end of that 10-year period. Okay. Now, there are also two other situations, okay? And these two situations really do come into play a lot as a consumer. The first is in the case of an auto loan, the example that I illustrated up front, okay? That auto loan is going to have us requesting a present value to purchase the vehicle. This is going to represent a positive cash flow. Jeez, I keep on doing that, don't I? So the present value is going to represent a positive cash flow because it's money that's coming into our pocket, and we're going to have periodic negative cash flows throughout the term of the expense. Now, I'm not even going to bother reviewing the equation for this present given annual or annual given present equation, because we simply do not need to concern ourselves with the equation itself, only the process that we go through to solve this type of problem. So we can say then that if we're looking for a present value, we are going to multiply the annual contribution by the present given annual at the interest rate and the specified time. Okay. Similarly, we can say that the annual contribution is going to equal the present value times the annual given present at the specified interest rate and the specified time. In this case, let's see how many or how much my annual contributions would be if I want to buy a $40,000 truck with monthly interest rates at 12% interest. And 12% interest is really high. But let's just say that that's the scenario we're faced with. So I want to find my payment values, my annual, if the present value of the vehicle I'm purchasing is $40,000. I've been looking at a pickup for a while now, and that's about the maximum I'm willing to spend on it. And if any of you have looked at the cost of pickups, you know that, holy cow, they can really get expensive really quick. Okay, my interest rate is going to be 12%. Okay, hopefully not. Hopefully my credit is strong enough so I can get a interest rate of maybe 4 or 5%. But this will just work out really well with our table. Okay, we're going to look at a monthly payment period. That means that we're going to be looking at 12 payment periods per year, and we're going to look at a 5-year term. Okay, so with this then, if we set up this problem, we're trying to solve for our annual contribution, in this case our monthly payment, given the $40,000 that we're taking out, times, let's see, just to set this up properly, we're looking at the annual given present, so that the present value here cancels the present value here, at the 12% divided by 12 months in a year, so 1%, and a payment term of 12 payment periods per year times the 5 years, so 60 payment periods total. So in this case, looking at my table, in this case my 1% table, in the annual given present column, we see that at 60 we have a multiplier of 0.0222. So we take 40,000 times 0.0222, and this gives us times 0.0222 gives us $888. Okay, so I don't know about you, but that just does not seem to be a workable amount. That is a sizable payment to make on this vehicle. So let's consider something else. What would happen if, let's say, we put $10,000 down on that vehicle? Okay. So in this case, we may choose to, I'm going to start a new piece of paper. I'm going to wrap this up really quick here because this gives you a really good idea of what we're going to be doing in Chapter 4. But let's say, just for the heck of it, that we run the same scenario, but we place a $10,000 down payment on that vehicle. So our present value now, instead of being 40,000, is 30,000. Okay. Everything else in the problem is the same. We still have the 1% monthly interest rate. We still have the 60 compounding periods. So we can go through and multiply this by the exact same multiplier, the 0.0222. And when we do so, we can see that this lowers our payments to $667. Okay? So by placing that $10,000 down on the vehicle, we saved ourselves a little over, or right around $220 on our interest, on our monthly payment. This is why down payments are so incredibly important, because if you do not place a down payment on a vehicle, ultimately what you find yourself doing is then you're going in and compounding a larger amount on a monthly period. And when you spread that payment over a significant length of time, that additional initial principal really adds up quickly. So, okay, so the other thing that we're going to introduce is what's known as a gradient series. Keep in mind that I did not do an example of a annual given present. However, it's the exact same process. I'm sorry, a present given annual. It's the exact same process. We determine what the present value is of a series of annual contributions, and we can go through and solve for it the exact same way. We just find the appropriate column in our table, plug in the multiplier that the table tells us to use, and we got it. Okay, so let's take a look at what's known as a gradient series. Okay, a gradient series is one in which we have cash flows, specifically annual cash flows, that are not uniform, meaning that they are increasing over some length of time. Okay, so in this case, we would say that we have a present value and a gradient annual contribution thereafter. So what we typically find ourselves doing is, when we go through here, we can say that, okay, well, we definitely have a uniform component, okay? This would represent a fixed annual contribution, okay? With that being a fixed annual contribution, then, then we can model this as one part a uniform payment series, okay, plus one part, well, and I won't include that because it's already included over here, of a gradient payment series, okay? So most generally when you work with these gradient series, you have to break them down into the uniform component and the gradient component. Anytime you're starting at an initial balance and incrementing from that balance each year, you're going to be running into this exact same situation. So as an example, let's say that we have maintenance on a machine that starts at $155 in the first year, and increases by $35 each year after that. Okay, so what we would do then, and let's just for the heck of it assume that the interest rate is 6% and that we're looking over a 7-year life cycle of this piece of equipment. Okay, so what we can say then is that if we want to find the present value of this investment, we can model it as money that we're putting aside now so that we can make these maintenance payments later on. In this particular case, we have what's known as an arithmetic gradient because it's increasing proportionally each time. In this case, we're increasing by the same amount from year 1 to 2, and by the same amount year 2 to 3, and so on and so forth. Jeez, I totally forgot to zoom out there for the beginning. Okay, as you can see, this is going to be broken down into two pieces. We have the uniform contribution, the $155 per year for the 7 years, and we have the gradient component that starts in year 0. Okay, so with this then, we're going to go through and say that the present value of this investment is the $155 times the annual given, of the present given annual at 6% for 7 years, plus the $35 gradient and we're looking for the present given a gradient value of 6% for 7 years. And with that being said, then now we can go and look this up in our table. When we do so, we find that the present value given an annual contribution, this is the uniform payment series part of this problem, is equal to 6% and present given annual. That is for 7 years. That is 5.582. So a multiplier of 5.582. And then from the tables, for a 7-year term, we have present given gradient, which is the last column in our table, 7 years, that is a multiplier of 15.45. So that would be the $35 times the multiplier of 15.45. And this gives us then $155 times the multiplier of 5.582 plus the $35. oh, excuse me again, the $35 times the gradient multiplier of 15.45 gives us a total present value of $1,405. This represents the amount that we have to put in savings in order to cover the maintenance costs for this piece of equipment for the 5 years. Okay, so this gives you a real good idea of what you'll encounter in Chapter 4. Again, I did not do an example of the future given gradient value. However, it's very straightforward. It follows the exact same approach. Keep in mind, for those of you that have not started on the coursework, it is important, extremely important, that you get going on that coursework right away. The class ends on the 22nd of August. If you are not done by then, you will receive the grade that you get. Ultimately, if you have 30% of the work done, then you'll end up with a 30% in the class. If you end up with all of the work done, then your grade will be reflected by that. But I will not, and I do not offer incompletes unless there is dire circumstances involved. So keep that in mind. I hope this has helped you with Chapter 4, and I will try to get the Chapters 5 and 6 introductions covered here fairly soon. So I will see you later.